In this section, we're going to talk about the reaction quotient Q. And everything we've been discussing so far deals with equilibrium constants. So here I have nitrogen gas plus 3 hydrogen gas in equilibrium with 2 ammonia gas. If we would want to write the K for this particular expression, it would be the concentration of NH3, that quantity squared, divided by the concentration of N2 divided by the concentration of H2 to the third power. And all of these concentrations right here, so all concentrations are equilibrium concentrations. So if we look at this graph here, and we look at the concentration of hydrogen, nitrogen, and ammonia as a function of time, here we have the concentration of hydrogen and nitrogen being consumed, and NH3 is going to be produced. Right about this point right in here, we can say equilibrium is reached. And notice that when we reach equilibrium, the concentration of hydrogen, ammonia, and nitrogen remain relatively constant. The question is, what happens to these concentrations here over on the left-hand region of our equilibrium dotted line? And how can we use those concentrations to predict whether or not an equilibrium is being reached? So we come up with something called the reactant quotient, which is Q. And Q is set up the same way as the K, which we have the concentration of NH3, that quantity squared, divided by the concentration of N2 times the concentration of H2 to the third power. For K, we have to have equilibrium concentrations, or the concentrations to the right of the dotted line in this graph. For Q, we can use any concentration. And that means that as a function of time, we can use this at any point in time. So for our K expression, we used equilibrium concentrations. For Q, we can use any concentration along any point of these in this particular graph. Okay? And what we can say is that K is a specific value of Q at equilibrium. And the values of Q and K can be compared to determine which direction a system will shift to reach equilibrium. So let's think about kind of an equilibrium well. And we know that equilibrium happens down here. And remember, equilibrium is a special point where Q is equal to K. So if we have a Q value greater than K, to reach equilibrium, a net shift from products to reactants must occur. So we're going to shift down this way from products over to reactants, or we can say there's going to be a shift to the left in a reaction involving A in equilibrium with B. If, on the other hand, Q is less than K, we can say that to reach equilibrium, a shift from reactants to products must occur, or we're going to shift to the right in order to reach equilibrium. So there's going to be a shift going this way. So by comparing Q and K, we can figure out where we are in terms of a particular reaction and which way that equilibrium will shift in order to reach equilibrium. So by varying these concentrations and changing these concentrations, we can see where we are in a particular reaction sequence, and this will allow us to predict how an equilibrium will shift. And in the next section, we're going to cover something called Le Chatelier's principle. And Le Chatelier investigated equilibrium into great detail and came up with a set of rules in order for us to figure out how an equilibrium will shift.